So now we want to look at the major class of reactions that carboxylic acids and acid derivatives do, and it's called nucleophilic acyl substitution. And acyl here means carbonyl, and specifically it's a carbonyl like here with a leaving group attached. So, and this does not include ketones and aldehydes. So for a ketone or aldehyde, the carbonyl carbon's either bonded to a carbon chain or a hydrogen, and they're never going to act as a leaving group. But in this case, we're going to have the carbonyl carbon either bonded to like a halogen or an oxygen or nitrogen, and they may not be great leaving groups, but at least you can call them leaving groups. Carbon and hydrogen are never going to be leaving groups. So in this case, if we look at kind of the general pattern of this reaction here, so it starts off the same way nucleophilic addition with ketones and aldehydes does, and it starts off with nucleophilic attack at the carbonyl. So, and if we kind of see what we get here, at least this is one way the mechanism can work. So you get this right here, and you still have your leaving group attached, I should say. And in this case, instead of actually just doing addition and protonating this oxygen, it turns out it's more stable if these electrons come right back down and kick off that leaving group, ultimately resulting in a substitution reaction rather than addition reaction. So now instead of the leaving group, now your nucleophile is attached in its place, and your leaving group has been left, I should say. Your leaving group simply left. And that's kind of the general pattern for this reaction. So it is a substitution rather than addition. You also are responsible for understanding the order in reactivity. So we're doing nucleophilic acyl substitution, reacting each of these with a nucleophile, which means they're the electrophile. They're electrophilic because that carbonyl carbon is partially positive. The only difference between all these different functional groups is the leaving group. So the more electron withdrawing it is, the more partially positive it'll make the carbonyl, and the better electrophile it'll be. So like with the acid chloride here, that chlorine's very highly withdrawing, leaving that carbonyl carbon to be very significantly partially positive, and the strongest electrophile in our rating here. If we look at the acid anhydride, on the other hand, he's bonded to an oxygen. So, and we found out with oxygen and nitrogen, they actually can be donating from a resonance sense, withdrawing from an inductive sense, but overall, they're not as withdrawing as a halogen. So a nitrogen being less electronegative is even less withdrawing than the oxygen. And so in this case, that's why the acid chloride is the most reactive, and the acid anhydride versus the ester. Well, it turns out with the acid anhydride, this guy is a little more withdrawing than with the ester, because the lone pair of electrons that could be donated, not only could it be donated towards the carbonyl of interest, it could be donated towards the other one. So overall, it's not as donating towards any given carbonyl, and so each carbonyl is a little bit more partially positive, not having as much electron density donated towards it, as is the case with the ester. And so esters and carboxylic acids are comparable, and then you've got amides, and with nitrogen being less electronegative, you can donate more by resonance, or you can withdraw less by induction, however you want to look at it. Now there's one other way we can approach this, and that's to look at how good is the leaving group. Well, in this case, chlorine is the best leaving group out of all the possible choices, and he's the best because after he leaves, he's the weakest base, the least reactive. Next on the list, this would be our leaving group here, and that's a carboxylate, and after it leaves, you'll have a negative charge in the oxygen. It'll be stabilized by resonance. Whereas with the ester or the carboxylic acid, so our leaving group will end up having a negative charge on oxygen, will actually be a strong base rather than a weak base like the carboxylate. And then finally, our amide here is our final, our weakest of the leaving groups listed, and it would be a very, 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 very strong base after it left, being the amide anion. So you could look at it again in terms of how electron withdrawing or donating each of these groups is, or how good of a leaving group they are after they've left. They'll lead you to the same trend. But we do expect you to remember this order of reactivity for these different acyl groups.